Here we go. So page 196, points of inflection. So you can see here that this will sort of follow our discussion from the other day here, but um, here you have a definition here. So let f be a function that is continuous on an open interval, and let c be a point in the interval. If the graph of f has a tangent line at c, f of c, then this is a point of inflection of the graph of f if the concavity of f changes from upward to downward or downward to upward. Okay, so now just try to think about what is going on here, that this is the point that we're talking about, this point here. So this is the value c, and so that would mean that this here would be f of c. All right, so we have here c f of c, and that's actually an inflection point. All right, so that's the point of inflection. So this is a point of inflection or inflection point. And then hopefully you can see that over here and right here we have some critical numbers, the relative minimum and relative maximum. All right, so these two would be the where the A and the B. All right, these would be where the critical numbers are at, because this is the relative minimum, there's a relative maximum, so we have two critical numbers. So now what you need to pay attention to is what else is going on with this graph. And then from over here to the point C, we see that the graph is sort of pointing in an upward direction. That's what we call concave up. So concave up. And then from C on, we see that the graph is sort of pointing in a downward direction, and that's what we call concave down. And so here, this is concave down. And so I see that the point of inflection is that point where the graph is changing from sort of an opening up or concave up direction to opening down or concave down. So now, similarly, here on the next graph, we have a point C, and then we have f of c, and then we have c f of c. But this particular one, this is actually an inflection point, because you can see again that the graph has an opening, a down, concave down direction over here, and then opening up, concave up sort of shape or direction over here. So this is concave down and concave up. So that point where the graph changes from concave down to up, or from up to down, is called an inflection point or point of inflection. But if you look at this particular graph, this one is a little bit different than the first one, because this graph is always increasing, and so it has no maximum or minimum. All right, at least not on the open interval, of course, and it also would not have any relative extrema anywhere. And so then we can look at the last one here, and we see here, if we call that point C, and this is f of c, so this is c f of c. This is an inflection point or point of inflection. So from here to here, the graph is sort of pointing upward, so concave up. And then over here, it changes to being concave down, all right? So here we have concave up, here we have concave down, and this particular graph is also always increasing and therefore has no maximum or minimum. All right, so I hope that you enjoyed that there. So let's actually go ahead and find the points of inflection, discuss the concavity of the graph of the function. So if you have any questions, please feel free to speak up or ask in the chat. But remember the rules for finding the concavity were let me review them. If I can't find the page, that's okay. So if the second derivative x is greater than 0, then that would mean that f is concave, right, concave upward on that particular interval. All right, so on an interval I, then f is concave upward on the interval. And if the second derivative is actually less than 0 on the interval I, then the f is concave downward. All right, so what I'm actually going to do now is go ahead and find the second derivative for f of x here. So the f of x is 2x to the third minus 3x squared minus 12x plus 5. So the first derivative is going to be 6x squared minus 6x minus 12. And then the second derivative is going to be 12x minus 6. And then I can go ahead and set this equal to 0. So that will give me my x-intercept of the second derivative. All right, so 12x is equal to 6. Then I divide by 12, so x is 6 over 12, which is a half. So that is, in other words, this is actually the critical number of f double prime of x, but it also means that this is a possible point of inflection. All right, so keep that in mind, that this is just a possible point of inflection. All right, so now what I'm actually going to do then is I am going to look at the graph of the f double prime of x, and I know that this was 12x minus 6, so it's a line with a y-intercept of -6, so 1, 2, 3, 4, 5, 6, and it has an x-intercept of a half, so there's the half. And so then, by the way, I also know that the slope was 12. So 1, 2, 3, 4, 5, 6. I know that there's a point at 112. But if I get my ruler out, and this ruler today comes from where I went to college at, Ferris State University, and it has a stress monitor on it. So, I mean, I guess I could try this right now. Hold the monitor firmly between your thumb and forefinger for 15 seconds. So I'll give you a chance to write this graph down. Well, you then will be able to see how stressed I am today. All right. So actually, I've always liked this ruler because of that. Just so that you know. So I'll let Howard. You can keep the time if it's been 15 seconds yet. So I'm assuming it is, and since I'm colorblind, I guess, well, that's not a good sign. It didn't change any color, so I guess that means tense. So that must mean that it's almost time for lunch, is what it really is. So if I go ahead and I graph that here, I see that over here the f double prime of x is less than 0, and over here the f double prime of x is greater than 0. So f double prime of x is less than 0, f double prime of x greater than 0. So what does that mean? Well, it means that on this interval from negative infinity over to a half, that f is concave down. All right, f is concave down on negative infinity to a half. And then you know that f then, because f double prime is greater than 0 over here, f is concave up on a half to infinity. So that answers the question of discuss the concavity of the graph of the function. But if you want to know whether the x equals a half is actually a point of inflection, well, if you look at this, you have to look at whether at x equals a half, f changed from concave down to concave up, or from concave up to concave down. So since f changed from concave down to concave up at x equals a half, that means that f has an inflection point at x equals a half. All right, so hopefully you enjoyed that. So before we do one last example of finding the point of inflection, does anyone have any questions about that? And I see that there's some more people who joined us. So, all right, so now, Victoria, how's it going? I see you're here now also. So now let's go to the next example. So now let's look at the, and by the way, if you need me to keep this up here longer, any questions again, please just ask. All right, so y is equal to x times the square root of 9 minus x. All right, so remember that if f double prime of x is greater than 0 on an interval I, then that means that f is concave upward on that interval, and otherwise if f double prime of x is less than 0 on an interval I, then that means f is concave downward on that interval. So I just want to be clear on the fact that that's why, again, we're finding the second derivative. All right, so now let's find the second derivative. So, by the way, just so that you're aware, like my different color pens came from Amazon, so I have all of these. So if one of them you think looks to show up on the screen better than a different one for you, you can just ask. I might not get the right one since I'm colorblind, but there you go. Like that's how fast they got here from Amazon. So if you think that it's kind of weird that the color sort of is changing, I'm personally just trying out different ones to see which one I think shows up better for all of you. But here we go. So to find the first derivative, we need to use the product rule. So we'll let u be x and we'll let v be the square root of 9 minus x, or 9 minus x to the 1/2 power. And so then u prime will be 1 and v prime will be 1/2 9 minus x to the negative 1/2 power times, we need the derivative of the 9 minus x because we're going to use the chain rule here. So that's -1. So don't forget to use the chain rule. All right, please don't forget that. So then using the product rule, All right, so again, we use the product rule. So if we use the product rule, then that means y prime is u prime v plus u v prime. So in that case, it will be square root of 9 minus x times 1 plus x times 1 half times 9 minus x to negative 1 half power times negative 1. And I might want to simplify this a little bit, but it is up to you because the fact of the matter is that we still have to find the second derivative anyway. So if I at least make it into something that looks like, well, I can multiply this square root of 9 minus x times 1 to get square root of 9 minus x. Then we have minus x over 2, or minus a half x, so minus 1 half x times 9 minus x to the negative 1 half power. And then, as always, it's up to you how you want to do this, but if you make this 9 minus x to the negative 1 half power uh, into an expression with a positive exponent, then it would be square root of 9 minus x minus 1 half x over, right, 9 minus x to the positive 1 half power. And then from here, you could go ahead and find the second derivative, or you can find a common denominator. But again, do you really want to do that if in the next step you are going to need to find the derivative again anyway? All right, so keep that in mind. So we have a y double prime. All right, so I'm going to actually at least write the square root of 9 minus x as 9 minus x to the 1 half power, just so that we're all clear on all of that. All right, so that I am actually going to change to a different color so that you know where my first derivative work ended, my second derivative work begins. All right, so what do we have here? We have the derivative of 9 minus x to the 1 half. So that's, again, 1 half. 9 minus x to the negative 1 half power times the derivative of 9 minus x again, which is negative 1. And then here we need the quotient rule. So we're going to use the quotient rule. And so, by the way, if you stayed over here, you could have used the product rule. So I don't really think it matters to me like which one you use, because it's going to be a mess regardless. All right. So if we use the quotient rule, then the numerator u will be x, the denominator v will be 2 times 9 minus x to the 1 half power. So u prime is 1, and v prime is 2 times a half times 9 minus x to the negative a half power. And then you need the derivative of the 9 minus x, which is negative 1. So again, the chain rule here. So now we have the quotient rule. So u prime v minus uv prime all over v squared. So that's what's actually going to go right here. So minus, oh, this is going to be kind of long here. So just try to make sure that you don't forget anything. And let me make this a little bit, oh no, one of the pens just fell on my foot. So we have a injury, and I don't know if I get workman's comp from working from my basement or not, but I guess I could apply for that and see what happens. So what do you really think happens when you have a workplace injury and you're at home? I really don't know. So now we have 1 times 2 times 9 minus x to the 1 half power minus uv prime, so x times, now this 2 times a half is 1, so I just have minus, so times minus, and that will be 9 minus x to the negative 1/2 power, all right, all over v squared, so 2 times 9 minus x to the 1/2 power squared. Woof, what a time to be alive, right? All right, so now let's go ahead and simplify this. So, all right, well, this is, in my opinion, quite a lot to simplify here. So, all right, so let's go ahead and look at this first part. So I'll bring this 9 minus x to the negative 1/2 power to the denominator so it can be written with a positive exponent. So it's negative 1/2. So negative 1/2 times 1 over 9 minus x to the 1/2 power. Then we have minus, all right, so 2 times 9 minus x to the 1/2 power. A negative x times a negative is actually a positive, so plus x, and then times, and I'll rewrite this as this 9 minus x to negative 1/2 power is 1 over 9 minus x to the 1/2 power, and then this is all over. All right, so we have 2 squared is 4, and 9 minus x to the 1/2 squared is just going to be 9 minus x to the first power. All right, so now I need to go ahead and see what the consequences of all of this are really. But if I go ahead and I simplify just a tad bit more, all right, so this will be negative 1 over 2 times 9 minus x to the half minus, and I'll go ahead and I'll distribute this minus at this point just to make it a little bit easier for me because of all the bracketing and things like that going on. But if I rewrite this so it's 2 times 9 minus x to the 1/2 over 4 times 9 minus x to the first, the minus, and then x times 1 over 9 minus x to the 1/2, and then I need to multiply by the reciprocal, so this is like over 1, so that means that this actually is 1 over 4 times 9 minus x over here as well. So there's definitely a lot going on, as you can see here. So we're not done yet. So, oh, what a time to be alive, right? Now, by the way, remember, all of this algebra is to simplify this so that we can set this second derivative equal to 0. All right, so I haven't actually done any calculus in about probably like 5 or 10 minutes. I'm still trying to do the algebra here. So now let's look at what we have here when I simplify this. So I have negative 1 over 2 times 9 minus x to the half minus, and then 2 over 4 is a half, so 1 over 2. But then I actually, if I look at this 9 minus x to the 1/2 over 9 minus x to the first, that's actually 9 minus x to the 1/2 in the denominator. So 1 over 9 minus x to the 1/2, and then minus x times 1 is x, and then we have 4 times 9 minus x to the, well, this will be 3/2 because it's 9 minus x to the 1/2 times 9 minus x to the first is 9 minus x to the 3/2. So hopefully you're all enjoying this exciting algebra here. And so then what I actually will do is I'll go ahead and I'll but believe it or not, like believe it or not, what I'll do here. Oh, by the way, I do think that's supposed to be a I think that's supposed to be a plus. I'm not sure what happened, but oh, you know what? I do see what happened because you all know this, but I will be quite honest with you that you all I think already know this, but this is not my fault. This is definitely not my fault because actually I think it's a minus. Okay, there we go. You caught me again. All right. So um now what are we going to do? So we are going to combine these two because they have the same denominator. So minus a half is minus 1. So minus 1 over the 9 minus x to the 1/2 power plus x over 4 times 9 minus x to the 3/2 power. All right. So then what are you what are you going to do next? All right. So now it's up to you. You really can think about this and just try to find a common denominator or whatever you want to do. And by the way, I think I was going to show you the graph of these derivatives here so that you could uh, see what it is. So because I feel like that might give you a hint also, but so let me see if I can bring up the graph because I feel like this is in my opinion a how do I put this a big mess. Hopefully you would agree with me that this ends up being how do I put this a big mess. All right, so now what are we going to do here? Uh, well, oh yeah, sorry. Did I say minus? I think I, I think I told you that. I think I told you I looked back and it was minus, and I have no idea. So one of the times I thought that this would seem strange to me. All right, so let's find a common denominator. So I'll show you the graph in a moment here. So let's actually multiply by the 4 times 9 minus x, 4 times 9 minus x to get the common denominator of 4 times 9 minus x to the 3/2 power. All right, so I'll distribute this is actually negative 4, so negative 1 times the 4 is negative 4, so negative 4 times 9, negative 36, then that will be negative 4 times negative x plus 4x, then we will have minus x. So then if I combine the like terms in the numerator, I have negative 36 plus 3x all over 4 times 9 minus x to the 3/2 power. So I really hope that you actually enjoyed this here, right? Because now we are about ready to set the second derivative equal to 0. So this is y double prime, remember, and so we're going to set this equal to 0. So now if I set this equal to 0, I just equate the numerator equal to 0, so negative 36 plus 3x equals 0. So then add the 36, so 3x is equal to 36. And then I'll divide by 3, so x is 12. So again, this is actually a possible point of inflection. Now, what I also want you to notice is that if you look at this, you know that, look at this denominator, all right? So you know that 4 times 9 minus x to 3/2 power cannot be equal to 0, right? So now I will, of course, divide by the 4 to make this a little bit easier for us. So it's just 9 minus x to the 3/2 cannot equal 0. But this is actually the square root of 9 minus x to the 3rd power cannot equal 0. So I already know then that if I cube each side, all right, so then I have the square root of 9 minus x cannot equal 0. And then I can go ahead and just think about what this means to me. And it means that what's under the square root, 9 minus x, has to be greater than or equal to 0. All right, so then I'll subtract the 9. So negative x has to be greater than or equal to negative 9. Then I'll divide by negative 1 and switch the sign. So x has to be less than or equal to 9. Well, since x has to be less than or equal to 9, that means that, well, what does that mean? It means that 12 cannot be a point of inflection. So we found a possible point of inflection, but it's not a point of inflection because the x has to be less than or equal to 9. All right, so keep that in mind that, well, since x has to be less than or equal to 9, that means that f has no points of inflection. All right, so we went through all that work to, again, just figure out that f has no points of inflection. Now, the other interesting thing for us is that if I look at the graph of y double prime, all right, now I'll just show you the graph of this real quickly. So I know that the x has to be less than or equal to 9. So here is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I can go ahead and substitute some points. So I'll make a table here just so that you don't think that I am trying to fool you here. Actually, you know what? I already have the values pre-calculated, but just for all of you, this is how much I like you. I will go ahead and I will calculate this here right on the spot. So let's see, we have negative 36 plus 3x over 4 times 9 minus x to the 3 halves power. And then if I want to figure out what this is at, say, 0, I get negative a third. And so here's 0, negative a third. And then let's look at, oh, well, let's try 8. All right, if I get 8 here, I have negative 3. So 8, negative 3. And then here's my graph. All right, it looks like this. So I can see then that y double prime is less than 0 on the whole interval here from negative infinity to but that actually should be less than 9 because but x is less than 9 since x cannot equal 9 because that would make the denominator equal to 0. Of course, I thought that in my head because look at this, I drew the asymptote. So that of course x cannot equal 9, but it's y double prime is less than 0 on the interval from negative infinity to 9. And so what does that mean? Well, that means that y is concave down everywhere, which means that it has no points of inflection. So f or y, all right, whichever one you want. This means that that y is always concave down and has no points of inflection. What a time to be alive, right? All right, so I hope that you enjoyed this example on finding points of inflection, but now we're going to switch gears a little bit and talk about the second derivative test. So does anyone have any questions before we talk about the second derivative test. I hope that, again, you're really enjoying this, because it's one of my favorite things to do. All right, so now it's time for the second derivative test, and here we go. So what is the second derivative test used for? Well, look at this here. If f is a function such that the first derivative at a point c is equal to 0, and the second derivative of f exists on an open interval containing c, then if the second derivative at c is greater than 0, then f has a relative minimum at c f of c. So you can see the diagram right here. At this point c, you can see that the first derivative is equal to 0 because of the horizontal tangent line here, right? But so that means f prime of c is equal to 0. But you also can tell that the second derivative is actually greater than 0 because f was concave up. All right, f is concave up. So then that means that that was a minimum here, which I did show you earlier when we first started this, that's sort of what we're looking for. Concave down will have a relative maximum in that interval, and concave up will have a relative minimum in that interval, but other things could happen as well, like f is always increasing, so no relative extreme, or f is always decreasing, no relative extreme number, or things like that, all right? So here, same thing. We have a point C where the first derivative at C was equal to 0, and so there's my horizontal tangent line. And then this graph is concave down, so the second derivative is less than 0. So f is concave down. So what does that mean? It means that f has a relative maximum at c f of c. All right, so you can see there is the relative maximum here. And then if the second derivative at c is equal to 0, then the test, when I mean the test, I mean the second derivative test is inconclusive. And so what do I mean by that? I mean that you should try some other test. So try the first derivative test. All right, so this is actually just a different way to figure out whether the function f has a relative maximum or minimum at a point. So use the second derivative test to find all numbers at which the function has a relative maximum or minimum. So here we go. So we'll find the first derivative of f of x equals x squared plus 2x minus 15. So that would be 2x plus 2. And then try to remember one thing, is that we need to find the second derivative. All right, so the second derivative is 2. So that means that this second derivative, f double prime of x, is greater than 0 because 2 is greater than 0. So now all of this tells us right now is that therefore f has no points of inflection because f is concave up everywhere. But remember, we're trying to figure out not the points of inflection. We're trying to figure out whether f has a relative maximum or minimum. So where do I find the points for the possible relative extremum? That's actually from the first derivative. So you use the second derivative to find the possible points of inflection, but you find the first derivative to figure out the possible relative maximum or minimum. So I need to set this first derivative equal to 0, and then I'll subtract the 2 and divide by 2, so x is -1. So this is a critical number for f. And so what I need to do then is actually just go ahead and say, well, all right, since f is concave up everywhere, then that would mean that this is actually going to be the relative minimum. All right, but let's verify this just so that you don't think I'm crazy. I'm going to take this point, all right, and then I'm going to substitute it in here, and so f double prime of -1. I'm going to take this number, substitute it in here. This is automatically equal to 2, and so that means that since the second derivative was positive at this number, that means that f has a relative minimum at x equals -1. So since the second derivative was positive at x equals -1, that means f has a relative minimum at x equals -1. All right, that's the second derivative test. Now, just as a reminder, like how does this compare to the first derivative test that we did last week? Well, here would be the first derivative test. All right. So this was the second derivative test. And this is how we figure out using the first derivative test. We would actually take the first derivative, and then we would actually go ahead and we would graph it. So here is the -1 for the x-intercept and y-intercept of 2, and then we would see that at x equals -1, the first derivative is changing from negative to positive. So that means that, all right, here f prime of x is actually, well, less than 0, and f prime of x is actually greater than 0. And so there we go. Like you can hopefully see there that if a graph is actually changing from negative to positive like if the derivative is changing from negative to positive at the point x equals -1, that means that x equals -1 is a there's a relative minimum at that point. So f is actually decreasing, and here f is increasing. So then we would say f is changing from decreasing to increasing at x equals -1. So f has a relative minimum at that point. Which one is easier to do, the second derivative test or the first derivative test? In my opinion, if the second derivative is actually easy to find, and it's not like that one with the square root in it that took us a long time to find, then it's not that difficult to use the second derivative test. Otherwise, I would probably stick to the first derivative test to try to save myself a little bit of work here. All right, let's try another example. So if you have any questions, please feel free to ask in the chat. But I think that the hardest thing is just to keep straight, like what do you use each derivative for? The first derivative to find the the critical numbers for f and the possible relative maximum minimums. In the second derivative, to find the possible points of inflection. And then what do you do with these? Well, the possible relative maximum minimums are only at the numbers where the first derivative is equal to 0. All right, so keep that in mind. So here is another great example here. So g of x is equal to negative x to the fourth plus 4x to the third plus 8x squared. So let's find the first derivative. So that will be negative 4x to the third plus 12x squared plus 8x. And remember, I need to set this equal to 0. So set equal to 0. So I'll factor out a negative 4x. So negative 4x times x squared minus 3x and plus 2 will be equal to 0. Then I'll factor again x minus 2, x minus 1 equals 0. And so then I'll set each factor equal to 0. So negative 4x equals 0, x minus 2 equals 0, x minus 1 equals 0. So x could be 0, x could be 2, x could be 1. So these are the critical numbers for g of x. Wait. Oh, yes, you're right. You're right. See now, you're right, because I can't multiply. I can't even do 2 times 8. So I'm glad that you said something. Thank you. All right, so this should be 16. All right. See, if I could do 2 times 8, we would be in business, right? So I know that, so that should be, what is that? So that should be, so if I could do 2 times 8, we would have a lot better situation here, wouldn't we? All right. So now, let's see. So that will be negative 4x times x squared minus 3x. Then that should be, what is that? Minus 4. That can't be right. Oh, yeah, minus 4. There we go. So now we have x minus 1, x minus 4, x plus 1. I think one of them actually was right. It's just that last number was not the correct value there. All right, so now that will be x minus 4 equals 0, so x could be 4. And then, oh no, now the whiteout is messed up. I told you this was not going to end well. All right, so now x plus 1 equals 0, and x will be negative 1. All right, so does anyone have any questions about that before we move on to what we would do with these values? Because like I just want everyone to make sure that you know what is going on here and that we're clear on this. And I just want to give you an extra second to make sure that you can read that, because I know that I actually have the blue or whatever color marker this is all over my hand now. So we have x is equal to 4, negative 1, and 0 then. All right, so now we need the second derivative. So the second derivative is going to be, well, the first derivative is right here. I'll try to circle it so that I don't multiply incorrectly again this time. So now we have, what's that? Negative 12x squared plus 24x plus 16. And then all we really need to do is, again, we don't need to set this equal to 0 because we don't actually need to find the inflection points. We just need to figure out which one of these are relative maximums and which one of these are relative minimums, or which one of these is neither. All right, so we don't need to set the g double prime of x equal to 0, since we're not trying to find the inflection point. So I want to be clear on that. We don't need to set this equal to 0. We're trying to find the relative maximum and minimums only. So g double prime of the first one, 0, will be negative 12 times 0 squared plus 24 times 0 plus 16 is 16. So at x equals 0, g double prime of x was actually positive. It was 16. So that means that g of x is concave up, and that means that g of x has a relative minimum at x equals 0. All right, so now let's do the next one. X equals 4. So we have g double prime of 4. So negative 12 times 4 squared plus 24 times 4 plus 16. So now let's go ahead and we'll go ahead and find this out. So that will be negative 12 times 16 plus 24 times 4 plus 16. That will be negative 80. So at x equal 4, g double prime of x is less than 0 because it was negative 80. So g double prime of x is less than 0. So that means that g of x is, so not g of x. G of x is concave down. So that means that g of x has a relative maximum at x equals 4. And then the last one was x equals negative 1. So g double prime of negative 1. So that will be negative 12 times negative 1 squared plus 24 times negative 1 plus 16. So that's negative 12 times 1 minus 24 plus 16, and that's negative 20. So at x equals negative 1, g double prime of x is actually less than 0. So g of x is actually concave down at that point, and so g of x has a relative maximum at x equals negative 1. There, I told you, like, that's how I got the last number at the top. I multiplied incorrectly because I didn't even see where we started at. So just so you're aware that this is what is going on. The problem did ask us again, just find all numbers at which the function has a relative maximum or minimum. So you could summarize g of x has a relative minimum at x equals 0 and a relative maximum at x equals negative 1 and x equals 4. All right, so are there any questions about this at all? All right, then that is it for this page. Is that Howard gets minus 500 points for not catching the mistake, and Abita, you get the 500 points. So tough luck, Howard. All right, so the next page is the application of inflection points. So now let's see. You can see that this is a normal distribution curve, and lots of people have been talking about the normal distribution a lot lately, just so that you're absolutely aware of what's going on. This is the normal distribution, or the just a bell-shaped curve, and what is going on is that you see the maximum is right here in the middle, and you can see the points where the graph is actually concave up and concave down, hopefully. So, I was actually going to show you this in color if I can find it, but I'm not sure if I can. So, oh no. Yeah, I'm not sure if I could actually find this. Yeah, you know what? That's fine. I don't have the color version, and now I can't even see how to get this graph I was looking up off of the screen, but that's okay. All right, here we go. So now here is the inflection point. Here is the inflection point. And so right here in the middle between the two inflection points, that's where 90 or wait, here 68.26% of the area under the curve lies. All right, and then you can see that in the next set between these two numbers, there's 95.46% of the values under the curve, and between these two values, 99.73% of the values under the curve, and so forth. But what's interesting here is that you can tell along this part here, the graph is concave down, and then you have the inflection point, and then the graph switches to being concave up. And then the same thing over here, the graph goes from being concave up to concave down. And so when you hear people talking about the flatten the curve or the normal distribution, and they show a curve like this is what you should be thinking about, that if like the distribution of any data is outside of this like distribution here, it's going to change the percentages. So that's how people are able to predict sort of like what is going to happen at say 1 week out, or how many people will be infected 2 weeks out, how many people will be infected, by looking at what the curve looks like, the number of people say infected at a certain point, and then calculating these areas under the curve like this using calculus techniques. All right, so keep that in mind, that this is what's going on in terms of how this would relate to all the graphs you might be seeing in the world today. So that's it for this section on inflection points. So hopefully you enjoyed that.